just for another chap. And then I saw her in the crowd and I looked her in the eyes.
I'm Jason.
I'm Sarah.
And I'm Catherine. Welcome to Castor in the Classroom's Stories from Sydney Observatory. We're up here on Observatory Hill in a dome at Sydney Observatory.
So in this session, we'll be telling you a little bit about the history of Sydney Observatory and explaining why the seasons, the eclipses, and the phases of the moon occur. Throughout this broadcast, you can ask questions. If you're signed into your Google account, you can ask questions using live chat. You can also ask questions via the Twitter handle by tagging @CITCVC and using the hashtag CITCOBS as shown on the screen.
So Sydney Observatory was built in 1858, but the site actually had a lot of uses previous to this, including housing a windmill, a fortress that was never actually used, and as a signal station. You might think that the observatory itself was built purely to observe the stars, but that's not quite true.
One person who knows more about this than anyone else is the curator here at Sydney Observatory, Dr. Andrew Jacob. Welcome. How are you?
I'm good. How are you?
Fabulous. So, Andrew, what was life back when the Sydney Observatory was first built?
Well, Sydney Observatory was built in 1858. It's almost 160 years ago. And life back then was very, very different. We're here on Observatory Hill today. We're surrounded by tall concrete buildings. The observatory is almost dwarfed by those. Beside us, we've got the Harbour Bridge. I can hear traffic running across that. And here we are web streaming on the internet in the modern era. So things back then were vastly different. There was essentially no electricity back then. The idea of electricity existed, but people didn't have electricity in their homes. That arrived later on for most people. You couldn't pick up a telephone and communicate with that. There was a thing called the telegraph. You could go to the post office and someone would tap out a Morse code signal to the other side of the world. But that had only just arrived. It was like the very latest mobile phone for everybody. It only just got here. What else was different? There was about 100,000 people in Sydney at the time, so the population was small. There were plenty of shops though, it was a busy place. There was plenty to do, but the way you did things, the way you experienced the world was quite different back then. If you went down to the harbour, you would see sailing ships. Maybe some steamships were around at the time, but mostly it was sailing ships. They'd bring in information and goods from the rest of the world. It was the only way to communicate was by actually writing a letter on a piece of paper, putting it in an envelope and sending it off in the post. So if you wanted to communicate with someone in England, it was a 3-month journey, 2 to 3 months at least, for the letter to get there, and you had to wait for someone to answer, another few months for it to get back. So that's
Far too long for me.
quite different.
But back then, what did people believe about questions like, is the Earth flat? Or how was the world created? Or even, what did our solar system look like?
I think people back then would have understood many of the things we understand now, except for the new bits of science that we've learnt since. So let me take them one at a time. Was the Earth flat? Well, actually, the ancient Greeks knew that the Earth wasn't flat. They knew the Earth was a globe. And throughout history, almost everyone has known that the Earth is a globe. It's in space of some kind. It's a bit of a mystery about the rest of the universe. But we knew it was a globe. Some people still think the Earth is flat. It's a bit funny, I don't understand why, but a few people think the Earth is flat still. Back then, most of the people in Sydney, the European people in Sydney, had travelled across the world in a sailing ship. They'd been over the edge of the world and they hadn't fallen off. They knew the Earth was a globe. So I think that's pretty simple. What did they believe about the formation, beginning of the world? Yeah. Well, a lot of people still went to church at that time and they still believed the Bible. Some people may not have believed it in a literal sense, but I think most people had this idea that God had brought the world into being. And there would have been some other beliefs as well, depending on where the people had originated from.
What about their beliefs about what our solar system looked like at that time?
Well, that's a good question, because back then we essentially knew most of the basics that we know now. We knew that the sun was the centre of the solar system and the planets orbited around the sun. That heliocentric model was known. We knew about the bright naked eye planets, the ones we can see by our eyes. People knew they were there orbiting around the sun. Uranus and Neptune had been discovered. Neptune had only just been discovered a few years before the observatory opened. So it was like one of these new, smaller planets we're finding around other stars now. It's just brand new, but it was there. Pluto was still up at 80 years in the future, so we didn't know about that, but we knew a dozen or so of the asteroids, and a handful of comets. So
Wow.
those basic elements of the solar system were well known and understood by people back then.
Amazing. And could you tell us maybe a bit about, at the time, what people believed about the creation of life and life here on Earth especially?
So as I mentioned, a lot of people would have taken the Bible's point of view. Perhaps not everybody believed literally the Earth and everything was created in 7 days. The ideas of science were coming through. The scientific revolution and the industrial revolution had happened some time before. So people's lives had been changed drastically by those. Their health, the way they travelled, the way they communicated was changing quite rapidly. And ideas of science, of rationality and looking at the evidence, making careful decisions and balancing the evidence you see. All those ideas were swirling around, were popular, people knew about them. So they may not have believed literally that the Earth had formed in 7 days. Maybe the ideas of Earth being around for at least millions of years, from geologists studying the rocks, those ideas were about. What else? So we're talking about the origins of life in the universe. Yes. So life was interesting. Now, just after the observatory was built in 1858, in 1859, Charles Darwin published his book On the Origin of Species. So this was another of these revolutionary things happening back at that time in the sort of mid-1800s. So he described us as having evolved from a common ancestor to the apes, and then having all life having evolved from some sort of common ancestor further back in time. So that idea just arrived on the scene as the observatory was getting going. So there was a lot of changes happening.
Very much so. And could you possibly tell us a little bit about, back at the observatory, the early history of this place, and tell us about the important people involved, so William Scott, for example.
William Scott was our first government astronomer, the first New South Wales government astronomer. It's a wonderful title. There aren't any government astronomers anymore, not from New South Wales anyway. Here's a lovely picture of William Scott. In fact, he was Reverend William Scott. He was educated in Cambridge in mathematics. He didn't learn astronomy until he got the job. He had the job about 2 years before he arrived in Australia. So he spent 6 to 8 months learning astronomy in great depth and a crash course in astronomy. Came out here. He was involved in selecting this site for the observatory on top of this hill, the highest point in the city area, which is a lovely place for the observatory to be. It suits its purpose. We'll come to that later. And he had an enormous number of things to do. He was given an enormous list by the Astronomer Royal at Greenwich in England. He had to measure the stars, their positions in the sky. He had to survey the state of New South Wales. He had to record the weather, and he arranged people around New South Wales to send weather readings to him. He had to take in visitors and show them around the observatory, and even help educate some of the new students from the University of Sydney, which had just been built as well.
Wow.
So it was a busy job for him.
Clearly.
From 1858.
So you've told us, Andrew, a little bit about the various roles that the observatory had. What would you say was its most important role at that time?
Its most important role was to tell the time. If you look at Sydney Observatory, you'll see on top of the observatory's tower is a large yellow ball, and that yellow ball rises up the mast just before 1 o'clock, and at 1 o'clock exactly it drops. So it's a signal to give everybody the exact time.
Okay, and I think we've actually got some footage of the observatory to show from the 1960s, so a little bit different than it is today.
Ago has always been a place where accurate time is essential. From 1858, the observatory has provided a service to navigators. The observatory, of course, is also used to observe, and this telescope has scanned the heavens as astronomers have studied the stars. Dr. Wood shows how photographs are taken and then put in this machine so the stars can be measured. And if you'd like to see the planets and stars close up, here's what they look like. This machinery is not for stargazing, it's for clock watchers. And the clock is a copper ball 6 feet in diameter. The time ball is controlled electrically. The ball replaced the first 1 o'clock gun because a visual signal was more accurate for skippers wanting to set their chronometers. It's almost 1 o'clock now. There it goes. A split-second time service from Sydney's old observatory.
So for us here at the observatory today, we actually just saw this time ball drop that you've been talking about. It dropped at exactly 1 o'clock, so about 40 minutes ago. how come 1 o'clock? Why not 12 noon or some other time?
1 o'clock was the best time to drop it for the following reasons. We have to work out the time in the first place anyway. So astronomers use the position of the sun to work out the time. We know that the sun's in the east in the morning, in the west where it sets in the afternoon or evening. At the middle of the day, at 12 midday, the sun is due north of wherever you are on the Earth. You can almost use it as a compass if you like. This midday, the sun is due north. And we have a telescope that points due north. It's very carefully aligned. We call it the transit circle, still in the observatory. It looks due north. When the sun crosses over the end of the telescope, and you can see the sun through the telescope, and you do that safely, of course, then you know it's midday. You know it's exactly 12 o'clock. But it's very hard to drop the time ball, get the time ball wound up and drop it, and observe the sun all at the same time. So the astronomer observed the sun at midday, waited 1 hour. It's a nice convenient time to drop the time ball. His assistant would go up, wind the ball up, and he would be able to release it, or he would let his clocks electrically release the time ball.
Well, I guess that makes sense then. But why was that useful? Didn't people have clocks and watches of their own?
Yeah, good point. Some people had clocks, a few people had pocket watches, no one had a wristwatch or a mobile phone. So telling the time for most people was not very easy. At least they knew once a day, when they saw the time ball drop, that it was 1 o'clock. Otherwise, they would just use the sunrise or the sunset, or the approximate position of the sun, perhaps, to give them an idea what the time was. Some people didn't need to know the time so accurately. The people who did need to know the time, very precisely though, were the ship's captains out in the harbour. They had chronometers, and they would watch their chronometers and compare their chronometers to the time ball. So if their chronometer or their clock on board ship was different from the time ball, they would know how to correct their time.
Okay.
Why did they need to know their time? One very important reason, ships could use those clocks in a slightly complicated way to work out their position on the surface of the Earth.
Oh, wow.
So as they sailed out of the heads and away from land, they were on the open ocean. There was no landmarks. There was no way to really know where they were. But their clock told them what the time was back in Sydney. And they could use that time in comparison what the sun was telling them to work out their position around the globe. Don't really have time to explain everything here, but it was important that they knew whether their clock was correct and how fast or slow it was going. The time ball told them that.
Okay, yeah, I can definitely see why keeping time at Sydney Observatory was so important then.
Definitely.
It does seem bizarre to those of us from, I guess, this century or this decade even, that clocks still needed to be set and were not accurate compared to our mobile phones where we just pull it out and there's the time.
Absolutely.
So we are in the East Dome today, and we do have a wonderful modern telescope here behind us. So what other telescopes has Sydney Observatory housed over the years?
Quite a few actually, some very nice ones as well. So in our south dome of the observatory, which was one of the first dome to be built here with the rest of the observatory and the time ball, we've got a lovely 30 centimetre diameter telescope. It has a magnifying glass 30 centimetres across. It's about 4 metres long. It's a wonderful telescope. It's the largest refracting telescope still in operation in Australia. We use it at night for visitors to come along and have a look through. And during the daytime, when school groups come along, we show them some objects on the horizon through that telescope. That's a lovely one. It's lovely that it's still in use as well. We have the transit instrument I mentioned, the one that is used to look for the position of the sun at midday. It works a bit like a fancy sundial, if you like. And we've got a few others. There's one other lovely old telescope, a small one about 4 inches or so in diameter, about as long as my arm, and that's from 1820. So it's almost 200 years old. And that one we don't use. It's way too fragile and valuable to actually look through. We've got that in the storage case. But it's lovely to have those. That's actually on site. We can see that one. But
Wow.
An amazing piece of history. So are there any significant astronomical or scientific discoveries that have actually been made here at Sydney Observatory?
Yeah, a lot of people ask me this question. I always have to say, well, no, nothing really spectacular or individual that stands out. Like one observatory in America found Pluto, and they're still talking about that today. You can go along and find out all about the equipment they used. But Sydney Observatory never really found anything spectacular like that. It was a working, practical observatory. These days we think of observatories as places to do astronomy, study stars, planets, look for life elsewhere in the universe. But back in the past, I mentioned Sydney's observatory was for measuring the time and distributing the time. William Scott had surveying to do, and that's related to the transit instrument as well, the transit circle. So these practical, useful purposes were what the observatory was really built for. Astronomy was needed to tell the time, and the astronomer had enough time of his own, didn't mean to throw that pun in, but astronomer had enough time to actually spend some time at night with his lovely refractor in the South Dome, looking at the stars and planets and looking for comets and so on. A couple of slightly more interesting pieces of work, not just routine astronomy looking at the planets. There was a transit of Venus. Captain Cook was looking for a transit of Venus from the South Seas before he came on to map the east coast of Australia in 1788. And there was another transit of Venus in 1874, and the astronomers here got that nice telescope in to look, the South Dome telescope, to look at that transit of Venus, to see Venus moving across the face of the sun. It doesn't have a lot of practical benefit, but it helps us know the distance between the Earth and the sun. And if you think about it, it's a difficult thing to measure. You need a big piece of string or a long ruler. But you can't really do that, of course. So we sit here, we observe Venus going across the face of the sun. A little bit of trigonometry, stuff you might have done at school, will help you understand from those observations the distance to the sun.
Wow.
Fascinating.
Yeah.
So I have heard that Sydney Observatory is no longer a working observatory. We've just been talking about some of the work it did do. So why is it still important to this day?
Yeah, Sydney Observatory closed down as a working observatory and a research observatory in 1982, and it became a museum, Museum of Astronomy and Surveying and Meteorology and a few other things, and a public observatory. And it's part of the Museum of Applied Arts and Sciences now, the Powerhouse Museum you may know about. So that was in 1982. And so nowadays we run tours at night for anybody to come along and have a look at the stars through our telescope, look at Saturn, which is really spectacular, or the moon. We have education school groups and so on coming in the daytime. And then visitors just visit us. During the daytime they can come in and have a look at our exhibits around the museum. So we're a museum, which means we have a lot of aspects of history. We talk about the history of astronomy and the science that's been done in Australia over the last few hundred years. And I think that's important because if you know the past, if you know what was done in the past and what happened in the past, you can understand the present, where have we come from, you know where we are now. And if you know where we are now, where we've been, you can understand where you're going to go in the future. You've got some background to help you plot a path into the future. I think that's pretty important.
Indeed, it sounds amazing. So before we move on to the next section, please do keep your questions coming in. If you have any questions throughout the show, please do tweet them or message them to us with the live chat.
Thank you so much, Andrew.
So one thing that's changed throughout the life of the observatory are the quality of the telescopes in it. This one here is a reflecting telescope, which means that it uses mirrors, a little bit like this one, to collect and focus the light. So telescopes like this allow us to make careful observations of objects in the sky, and that in turn allows us to better understand things like our solar system, our galaxy, and the universe around us.
Yes. So science is all about taking new data and using it to test our ideas and existing models. And if the model doesn't fit what we observe, then we have to change that model to come up with a way to fit the data that we've actually observed. And this is a continual process and a constant quest for truth that drives all scientists.
Although before astronomy was really able to explain the seasons, a lot of different cultures had various myths that they used to explain what they observed with the seasons. For example, according to ancient Greek mythology, Persephone was the daughter of Demeter, the goddess of the harvest. Now, Hades was in love with Persephone and stole her away down into the underworld where he stayed. Now, Demeter was searching everywhere that she could for her daughter, and it was only until the god of all gods, Zeus, told Demeter where Persephone was that they had to decide on a solution. And essentially, they decided that for 6 months of the year, Persephone would stay down in the underworld with her now husband Hades, and for the other 6 months of the year she would return up to the surface with her mother Demeter. Now for the 6 months that Persephone was down in the underworld, Demeter was obviously so upset and sad at the loss of her daughter, so all the plants would wither and die. But when Persephone returned, Demeter was so ecstatic and happy that these plants could grow and thrive. That's how they explain the seasons of winter, summer, autumn, and spring. And I think that's a pretty beautiful myth.
So it is a great story, but it's not exactly why the seasons happen. So before we continue, we do have a multiple choice question for you. So the question is, true or false? Seasons are caused by the changing distance of the Earth from the Sun during the year. So we'll give you a couple of seconds to think about that, and feel free to tweet or live chat those answers towards us. Okay, so if you answered false, well done. It's true that the Earth's orbit around the Sun isn't a perfect circle, but that's not the reason why we have the seasons.
Actually, it's a combination of both the Earth's orbit around the Sun and the fact that it rotates on a tilted axis. So, for example, if you imagine this Earth has a line going straight through the poles, through the center of the Earth, and now imagine that that line is tilted 23.5 degrees from the vertical. Now, that is how it orbits around the Sun on that axis.
So again, a lot of people think that the fact that one hemisphere is closer to the Sun than the other is what causes that difference in temperature between summer and winter. But again, that's not the case. So what's actually happening, it's to do with the way that the Sun's light falls on the surface of the Earth. So in summer, the Sun's light falls on a much smaller surface area of the Earth, whereas in winter, it falls on a much larger surface area because of that tilt. And so that is what actually causes the warmer temperatures in summer and cooler temperatures in winter.
Wow. And I guess here's something to think about as well, guys. What would be the case if that was tilted even further than 23.5? Imagine, for instance, the Earth was tilted at, say, 35 degrees. How would that change the weather where you live? Or even if it wasn't tilted at all, what would happen in that case? If you have any answers, guys, again, don't forget to tweet us or put it in the live chat.
So as well as this, as the Earth orbits around the Sun throughout the year, we see different parts of the night sky. And because we're seeing different parts of the night sky, we're also seeing different constellations. Now, we've got some images that are going to come up on the screen in a moment, which show the sky from Australia shown at different times throughout the year. So in ancient times, the changing sky was how people knew what time of year it was. And they used these constellations as a form of calendar. So it helped them know, for example, the best time to plant crops, when to harvest these crops, and even the best times not to go in the ocean because it was shark breeding season.
So we see the stars moving throughout the course of the night and also changing throughout the course of the year as the Earth orbits the Sun. So that tells us that one of two things is happening. Either the Earth must be moving or everything else around us is. And now we know, and it's kind of obvious when you think about it, that it's the Earth that would be the one that's moving. It doesn't make sense that the billions of stars that make up our galaxy would all be moving around us.
But for a long time, people actually did believe in this geocentric model. They believed that everything would move around a stationary Earth. Now, observations of the night sky using telescopes just like this were really what helped prove that this couldn't be correct. And one of the main issues with the geocentric model was that it couldn't really explain this retrograde motion of the planets. Now, that's the motion where these planets seem to almost unexpectedly move backwards across the sky. And it was really confusing for a long time until we realized that there's actually a heliocentric model of our solar system. And this model was able to not only explain this motion, but correctly predict the motion of these planets across our night sky.
So it was Nicholas Copernicus who first seriously considered this model in a mathematical way and brought this theory into the realm of science. So the most important aspect of this heliocentric model is the key force that drives all of the motions of the planets, which we call the gravitational field. So in 1687, the brilliant English mathematician Isaac Newton had an apple drop on his head and this sparked an epiphany. So Newton published his, well, probably his most famous work, the Principia, and in it he described his universal law of gravitation, which defined the force of attraction between any two masses.
Does that mean if any two masses have a force of gravitational attraction between them, does that mean there's a force of attraction between us right now?
Well, technically yes, but fortunately gravity is actually such a weak force that any gravitational attraction between you and I would be incredibly small, too small to notice. But for something like the sun, even though it's actually only an average sized star compared to some of the other stars out there in the sky, it's massive compared to the Earth and the other planets in the solar system. So that means that its gravitational field is strong enough to hold all of the planets and other things like comets and asteroids in orbit around it.
Wow, and I guess on a much smaller scale, you can actually see the same thing. So for example, if you observe Jupiter, you can see it's, 60 odd moons orbiting around Jupiter, all held into an orbit because of Jupiter's gravitational field. You can even see the same thing with Saturn and its moons and its rings, and it's actually really great because you can see it with telescopes just like this one here, or even in a telescope in your own backyard. So it's pretty fantastic to observe with these telescopes. Even a little bit closer to home, if you don't have a telescope, we can see our nearest astronomical object, the Moon, which is held in orbit around the Earth by its gravitational field.
So every now and then, the relative positions of the Sun, the Moon, and the Earth result in a phenomenon we call eclipses. And there are two different types of eclipses. There are solar eclipses and lunar eclipses. Now, a total solar eclipse is where the Moon passes directly between the Earth and the Sun, blocking out the light of the Sun from our view. Now, solar eclipses are amazing to view, but of course, if you ever do get the chance to view one, please make sure that you're careful and you wear special eclipse glasses when you're looking at it, because you don't want to damage your eyes whilst the sun is out.
Very true. So a solar eclipse is different though from a lunar eclipse, where the Earth now passes directly between the sun and the moon, and that means that the sun's light can no longer reach the moon, it doesn't shine on it, and so the moon goes into darkness.
Now, the relative positions of both the Earth, the Moon, and the Sun also give rise to the phases of the Moon. So, for example, if I were to have the Moon in between the Sun and the Earth, the illuminated side, there's only one side which is illuminated of the Moon at any one time, and that illuminated side in that position is facing away from us. So we actually can't see the Moon at all. That's a new Moon. But as the Moon goes through its orbit and the Earth moves around the Sun, this changes and we start to see more and more of the illuminated side. So the Moon grows larger and larger until it gets right around to the other side where we see a full moon because the illuminated side is now entirely facing us.
Oh, cool. So here's an image of the moon taken from Sydney actually yesterday. So take a look, guys, and see if you can figure out what phase of the moon it is right now and what that means in terms of where the Earth and the Sun and the moon are relative to each other. Again, you can tweet us your answers or send them through live chat.
So that was a really nice video just there where you could see those phases of the moon changing as the moon went around in its orbit. And here's the photo of the moon from last night. Let us know what you guys think.
Brilliant.
So that's the scientific explanation about the phases of the moon. But it's really important to keep in mind that almost every culture throughout history has had its own explanations of this and other astronomical phenomena.
In fact, one example of this is the ancient Egyptians who believed that the sun god Ra was carried across the sky in a boat and at night time was carried through the underworld only to emerge again at sunrise, past the underworld back to the world of the living, I guess. And there was also a story from the Inuit of Greenland, Inuit means people, where they believed that Anagan, who is the god of the moon, would continually chase his sister Melina, the sun goddess, across the sky. Now, during this chase, he gets hungrier and hungrier, and so he slowly gets thinner and thinner. Now that's what causes the crescent moon, as it's slowly getting thinner and thinner, until basically Onegin realizes that they need to have a break for food. So takes a 3-day break from chasing his sister and fills up his belly, and that's a new moon where we don't see the moon for 3 days, roughly. And then he returns again to chase his sister and slowly get larger and larger, or as a larger moon, and basically continually chasing his sister throughout the orbit, which is a really lovely explanation.
Absolutely. So, although we now have scientific explanations for all of these phenomena and we can understand much better what is actually going on, I think it's really important that we never lose these other interpretations from cultures and ancient civilizations all around the world. They're still very important to keep in mind.
Exactly.
So thank you everyone for joining us here on Castor in the Classroom, Stories from Sydney Observatory.
So don't forget to look up every now and again. And if you have any questions after today's session, please do feel free to keep tweeting or live chatting those questions to us, and we'll answer them afterwards. Thank you.
Thank you.
Thanks, guys.
You came walking a long way and you were cold with rolling dust. Your eyes were staring at me while playing your guitar.
I come walking a long way just for another chapter.